Sir, and this will be a tutorial video of simple harmonic motion and elasticity, and this will be what we will be discussing 10.1 to 10.8. So reading the example, when a tire pressure gauge is pressed against a tire valve, as in figure 10.2, the air in the tire pushes against a plunger attached to a spring. Suppose the spring constant of the spring is K equals to 320 newtons per meter, and the bar indicator of the gauge extends 2.0 cm when the gauge is pressed against the tire valve. What force does the air in the tire apply to the spring? So this is the figure, as you can see. And the next is simple harmonic motion and the reference circle. Reading the question, the diaphragm of a loudspeaker moves back and forth in simple harmonic motion to create sound, as in figure 10.11. The frequency of the motion is F equals 1.0 kHz, and the amplitude is A equals 0.20 millimeters. So this is figure 10.11, and our question is, what is the maximum speed of the diaphragm? And where is the motion does this maximum speed of? So the solution for A would be V max equals A omega equals to the values that are given, which is this 0.20 times 10 raised to negative 3 meters multiplied by 2 pi multiplied by 1.0 times 10 raised to 3 hertz, which would give us the answer 1.3 meters per second. And for our B, as you can see, the answer is x equals to 0 meter because it is at rest. Here we have energy and simple harmonic motion. Ball is attached to a vertical spring, as in figure 10.19. The spring constant of the spring is 28 newtons per meter. The ball, supported initially so that the spring is neither stretched nor compressed, is released from rest. In the absence of air resistance, how far does the ball before being brought to a momentary stop by the spring? So this is 10.19. So for our solution, as you can see here, E final is equals to E initial. So we would just derive, and this will be our final working. HO equals 2 mg over K, which is equals to the values 2 multiplied by 0.20 kg multiplied by 9.8 meter per second square, which is our H, over 28 newtons per meter, and it would give us the final answer of 0.14 meters. Our next example is the pendulum. Figure 10.21 shows a clock that uses a pendulum to keep time. Determine the length of a simple pendulum that swings back and forth in simple harmonic motion of period of 1.00 seconds. And working being L equals T squared multiplied by G over 4 pi squared. G is given since the pendulum is moving back and forth, and that would give us the values of 1.00 seconds squared multiplied by 9.80 meter per second squared over 4 pi squared, and would give us the final answer of 0.248 meters. Next is 10.7, which is elastic deformation. Reading the example, a circus performer supports the combined weight of 1,080 newtons of a number of colleagues. See figure 10.18. This is 10.28. Each thigh bone of this performer has has a length of 0.55 meter and an effective cross-sectional area of 7.7 times 10 raised to negative 4 meters square. So, the question is, determine the amount by which each thigh bone compressed under the extra weight. And our solution to that would be using the formula L equals FL over YA, given by the values 540 newtons times 0.55 meters over 9.4 times 10 raised to 9 Newton meter squared times 7.7 times 10 raised to negative 4 meter squared, which would give us the final answer of 4.1 times 10 raised to negative 5 meter. And our last example is 10.8, which is stress, strain, and Hooke's law. And reading the example, human bones also follow Hooke's law for stress and strain, as indicated in figure 10.33. This is essentially figure 10.32, where we plot the stress versus strain specifically for a human femur, the largest bone in the body. So, in section 6.9, we plotted the average force versus displacement for a variable force. The area under the curve was equally to the work done by the force. Now let's apply a similar analysis to 10.33, and the question is, calculate the area under the curve where Hooke's law is valid, which is the shaded region, and use unit analysis to describe what this area represents. So this is the working. As we can see here, it is a triangle, and just using the area for a triangle, which is half times base times height, which gives us the values of half times 0.010 times 200 times 10 raised to 6 PA, which give us the final answer of 1.00 times 10 to the power of 6 PA. And that is it, sir, and thank you.